There is a moment, and every astronomer who has lived through one will tell you this, when the universe stops being a place you study and becomes a place that is watching you back. It is the moment when a data point refuses to fit the model, when the numbers come back from the telescope and someone in a quiet room somewhere says out loud to no one in particular, "That cannot be right, check it again." And then they check it again, and it is still there, and the number is still wrong, and the universe is still watching. That moment happened on July 1st, 2025, and the object that caused it has a name that sounds almost bureaucratic in its plainness: 3I/ATLS, the third interstellar object ever detected passing through our solar system. Discovered by the Atlas Survey Telescope network, the same system that was built specifically to catch things before they hit us. The name tells you almost nothing about what the object actually is, which is, in some ways, appropriate, because what the object actually is, that is a question that planetary scientists, astronomers, astrochemists, and more than a few people who don't usually work in any of those fields have been arguing about ever since. And the argument, once you understand what they are actually arguing about, is one of the most extraordinary conversations in the history of human science. Let me set the stage for you, because the stage matters. We live on a planet that orbits a middle-aged yellow star in the outer suburbs of a fairly unremarkable spiral galaxy. We have been looking at the sky for as long as we have had eyes. We have cataloged billions of stars, millions of galaxies, hundreds of thousands of asteroids, thousands of comets, and enough cosmic debris to fill the imagination for several lifetimes. We have sent probes to the edges of our solar system. We have landed on the Moon, touched down on Mars, skimmed the atmosphere of Jupiter, and threaded spacecraft between the rings of Saturn. We have mapped the cosmic microwave background radiation, the literal afterglow of the Big Bang, with an accuracy measured in parts per million. We thought we knew, if not everything, then at least the broad outlines of everything. We thought the solar system was familiar territory. Then 3I/AT/Atlas arrived, and it turned out we did not know very much at all. To understand why this object is different, why it is not just the third interstellar visitor, but potentially the most significant astronomical discovery in human history, you need to understand what came before it. You need to understand 1I/Oumuamua and 2I/Borisov, the first two interstellar objects we ever detected, because they are the measuring stick against which 3I/Atlas is being judged. And 3I/Atlas makes both of them look, in retrospect, like practice runs, like the universe sending us warm-up acts before the main event. The story of Oumuamua begins in October 2017 at the Haleakala Observatory in Hawaii, where astronomer Robert Warwick was doing what astronomers do, systematically surveying the sky with the Pan-STARRS telescope, looking for things that move. Telescopes are extraordinarily patient instruments. They gather light over long exposures, building up images of faint objects that no human eye could ever detect directly. And in the data from October 19, 2017, something appeared that moved the wrong way. Its trajectory was hyperbolic, meaning it came outside the solar system, swung around the sun, and was heading back out again. It was the first object ever confirmed to have originated in interstellar space. They named it Oumuamua, a Hawaiian word that roughly translates to scout or messenger from afar. The name, as it turned out, was more apt than anyone initially realized. Oumuamua was strange. We could not get a good image of it because it was already departing when we spotted it, moving at about 87 kilometers per second relative to the sun. We could only study it through its light curve, the pattern of brightness changes as it rotated and reflected sunlight. And that light curve was extraordinary. The brightness varied by a factor of 10, which means the object was either extremely elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a flattened disk, or it was tumbling in a very particular way. It was reddish. It was dry. No water ice, no coma, none of the outgassing you would expect from a comet. But here's the part that shook the astronomical community to its foundations. Oumuamua was accelerating, not decelerating the way gravity would slow it down. Accelerating. It was speeding up as it moved away from the sun. And when you ruled out every known physical explanation for that acceleration, solar radiation pressure, thermal recoil from outgassing, magnetic sail interactions, you were left with something uncomfortable. You were left with nothing, no explanation that fit. The acceleration was there, the cause was not. Some scientists proposed exotic explanations. Hydrogen outgassing that was somehow invisible. Light sail dynamics for an object of unusual geometry. A few scientists, most notably Harvard's Avi Loeb, went further, suggesting carefully that the possibility of artificial origin could not be entirely ruled out. Most of the community did not go that far, but the acceleration remained unexplained. Oumuamua departed our solar system with its secrets intact. Then, in August 2019, came 2I Borisov, named for amateur astronomer Gennady Borisov, who spotted it from his backyard observatory in Crimea. Borisov was, at least superficially, less mysterious. It was a comet, a real, actual comet, with a coma in a tail and outgassing exactly the way comets are supposed to outgas. It was compositionally similar to comets from our own Oort cloud, with one striking exception. It had an unusually high ratio of carbon monoxide to water, suggesting it formed somewhere much colder than anything in our solar system. Borisov came from a different star around a different system, probably billions of years old, and it was nearly indistinguishable from local comets, which told us something profound. Chemistry might be universal. The building blocks of comets might be the same everywhere. The cosmos, at least at the level of icy bodies, might be more uniform than we thought. Two objects. One cigar-shaped, dry, anomalously accelerating, unlike anything in our catalogs. One comet, reassuringly familiar, chemically slightly unusual but broadly recognizable. Two data points, two windows into the interstellar medium. The scientific community processed them, debated them, published hundreds of papers about them, and waited, because the expectation, based on models of how often interstellar objects should cross through the solar system, was that we would eventually detect more. The LSST, the Legacy Survey of Space and Time at the Vera Rubin Observatory in Chile, was being built specifically to find them more systematically. The detection rate was expected to pick up. Nobody expected 3I ATLS. The Atlas Telescope Network, the Asteroid Terrestrial Impact Last Alert System, is not a glamorous instrument. It is not the James Webb Space Telescope, gleaming and golden, gazing at the dawn of the universe from 1,000,000 miles away. Atlas is a workhorse, a planetary defense system, a set of relatively modest telescopes spread across Hawaii, Chile, South Africa, and the Canary Islands that takes images of the entire sky every night and looks for things that are moving, things that might be heading toward Earth, things that might be problems. It is an early warning system for the kind of cosmic accident that ended the dinosaurs. And on July 1st, 2025, one of those telescopes caught something that was, in its way, more alarming than any asteroid. The object was already bright when it was detected. Not bright in the way that stars are bright, not visible to the naked eye, not yet, but bright relative to what it should have been at that distance. It was coming from the direction of the constellation Perseus, inbound at a steep angle to the ecliptic plane, the flat disk of the solar system where most of our planets and asteroids live. Its trajectory was hyperbolic, obviously hyperbolic, dramatically hyperbolic. When the initial orbital calculation came back, the eccentricity was 6.8, nearly 7 times more energetic than a parabolic orbit, which is itself the mathematical boundary between a bound solar system object and a free-flying interstellar one. Oumuamua had an eccentricity of 1.2, Borisov had an eccentricity of 3.36. An eccentricity of 6.8 was not just unusual, it was staggering. It meant this object was moving through the solar system so fast with so much kinetic energy that the sun's gravity was barely a nuisance. The speed confirmed the eccentricity. 3II Atlas was approaching at approximately 67 kilometers per second relative to the sun at detection. Faster than Borisov, though somewhat slower than the most extreme velocity for Oumuamua. At that speed, the entire crossing of the solar system, from the outer reaches to perihelion and back out again, would take less than a year. This thing was not browsing, it was passing through. Word spread through the astronomical community with the particular velocity that significant discoveries travel in the age of email and pre-print servers. Within hours of the initial report, telescopes around the world were being pointed at 3I by ATLS, the Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Hubble Space Telescope, which had to wait for a scheduling window, but got one faster than usual because the people who allocate Hubble time understood that this was not a request that could wait. Amateur astronomers with serious equipment picked it up within days. The Rubin Observatory, which had only just completed its first light operations, contributed data. The European Southern Observatory coordinated an international response. And what all of those telescopes began to reveal as the data accumulated in the days and weeks after discovery was an object that confounded every expectation. Let's start with the size, because size is the first thing everyone asks about, and the size of 3I by ATLS is the first thing that demands explanation. Based on its brightness at the time of discovery and the assumptions about its reflectivity, its albedo, the object appeared to be somewhere between 1 and 5 kilometers across. Let me be precise about what that means, because in astronomical discussions, the word large gets used so casually that it loses its weight. 1 kilometer is 6/10 of a mile. 5 kilometers is 3 miles. Manhattan is about 13 miles long, so we are not talking about something Manhattan-sized. We are talking about something the size of a small town or a large university campus, or, and this comparison is the one that tends to make people quiet, the size of the object that 66 million years ago ended the Cretaceous period and killed 3/4 of all species on Earth, including every non-avian dinosaur that had ever lived. The Chicxulub impactor, the asteroid that hit what is now the Yucatan Peninsula and triggered a global environmental catastrophe, is estimated to have been approximately 10 kilometers across, 6 miles. 3I by ATLS at its lower size estimate would be 1/10 that mass. At its upper estimate, it would be half that mass. It would not end all complex life on Earth if it hit, but it would end civilization as we know it without much effort, and it would do it in an afternoon. Now, 3I by ATLS is not going to hit Earth. Let me be clear about that. The orbital calculations, refined within days of discovery and then refined again and again as more observation points were added, show a trajectory that will bring the object to perihelion, its closest approach to the Sun, in late 2025 at a distance of roughly 0.5 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. Half an astronomical unit is roughly 46 million miles. The object's closest approach to Earth will be somewhat larger than that, and it will not come anywhere near Earth's orbit in a dangerous sense. It is not an impactor, it is a visitor. A very fast, very large, very strange visitor. But the reason its size matters is not about impact risk. The reason its size matters is about what it tells us about where it came from and what it is. Because 3I Atlas, at the sizes being estimated, is not just large for an interstellar object, it is large compared to most objects in our own solar system. It is larger, by some estimates, than anything in the Kuiper Belt, except for the very largest dwarf planets. It is larger than all but a handful of known comets. If the size estimates are correct, this is not a chip off an old block. This is not a fragment ejected from some distant planetary system by a gravitational interaction billions of years ago. This is a substantial body, a world unto itself, or something close to it. In a substantial body of this size, moving at interstellar velocities raises questions that planetary scientists are only beginning to formulate, let alone answer. The brightness. Let's talk about the brightness, because the brightness was the second thing that alarmed people, and in some ways it is more alarming than the size. 3I Atlas was brighter than expected when it was first detected, not just slightly brighter, dramatically brighter. And as the weeks went on and the object moved closer to the Sun, it got brighter still. This is not unusual for comets. Comets brighten as they approach the Sun because the solar heat sublimates their ices, releasing gas and dust that reflects sunlight and creates the characteristic coma and tail. So brightening was expected, but the rate of brightening, in the way it brightened, was not. The object developed a coma, a diffuse cloud of gas and dust surrounding the nucleus that was, by October 2025, several 100,000 kilometers across. To put that in perspective, the Sun is about 1.4 million kilometers in diameter. The coma of 3I Atlas at its most extended was approaching a quarter the diameter of the Sun. You could fit multiple Earths inside it. It was not the largest coma ever observed. Some great comets have produced comas comparable in size, but it was large, and it was actively evolving, and it was doing so in ways that suggested an unusually volatile composition. Volatility, in the language of planetary science, does not mean explosive in the everyday sense. A volatile compound is simply one that sublimates easily, turns from solid to gas at relatively low temperatures. Water ice is volatile. Carbon dioxide ice is more volatile. Carbon monoxide ice is extremely volatile. Nitrogen ice, as found on Pluto, sublimates at temperatures close to absolute zero. The more volatile your composition, the more actively you outgas when you approach a star, and the brighter and more active your coma becomes. The exceptional brightness and rapid coma development of 3I Atlas suggested that it was not just a water ice comet, like most of the comets we see in our solar system. It suggested something richer, something colder, something that had formed or spent significant time in conditions much colder than anything in our neighborhood sun.
The spectroscopic data, the chemical fingerprint taken by breaking the object's reflected light into its component wavelengths, began to come in within the first month of observation, and the fingerprint was extraordinary. There were the expected water signatures, there was carbon dioxide, carbon monoxide in quantities that were elevated even by Borisov's unusual standards. There were nitrogen compounds. There were complex organic molecules. Not life, let me be clear, not biological molecules in any sense that would suggest biology, but organic in the chemical sense, meaning carbon-based compounds of the kind that form naturally in cold, radiation-bathed environments and that are the precursors, in many models, of the chemistry that eventually led to life on Earth. The molecular inventory of 3I-Atlas, as it emerged piece by piece from the spectroscopic analysis, looked like a catalog of the most exotic cold chemistry environments that planetary scientists had ever documented. And then it contained things that were not in any such catalog. Molecular signatures that corresponded to no known interstellar compound, and that the analysis teams were still, months after discovery, working to identify. There is one chemical signature that deserves its own extended discussion because it is the signature that changed the conversation from unusual to unprecedented. That signature is deuterium, or more precisely, the deuterium to hydrogen ratio, what scientists call the DH ratio, in the water ice and water vapor coming off 3I-Atlas. And to understand why the D to H ratio matters so much, you need to understand a little bit of nuclear physics that you might not have thought about since high school, if you thought about it at all. Hydrogen is the most common element in the universe. A hydrogen atom, in its most common form, consists of one proton and one electron. Simple, clean, the lightest element. But hydrogen has isotopes, variants where the nucleus contains not just a proton, but also a neutron. An atom with one proton and one neutron is called deuterium, sometimes called heavy hydrogen. An atom with one proton and two neutrons is called tritium, which is radioactive and relatively rare. Deuterium is stable, and it exists in nature, but it is rare. For every 100,000 ordinary hydrogen atoms in the universe, there are only about 2.6 deuterium atoms. That ratio, 2.6 deuterium atoms per 100,000 hydrogen atoms, is called the primordial D to H ratio, and it was set during the first few minutes after the Big Bang, when the universe was hot enough and dense enough to fuse hydrogen into heavier elements.
That elevated D over H ratio tells a story. It says that the water ice in 3I/Atlas spent an extraordinarily long time, perhaps billions of years, in conditions colder and more isolated than anything in our solar system. It says this object did not form recently in a warm system similar to ours. It says it formed somewhere cold, or spent most of its existence somewhere cold, or both. And it has implications that planetary scientists are still working through, because those implications connect not just to where this object came from, but to the broader question of how chemistry propagates across the galaxy. If water with this D over H ratio can be carried across interstellar space by objects like 3I-Atlas, then perhaps the chemical seeds of life, not life itself, but the precursor chemistry, can be scattered across the galaxy by the same mechanism. Perhaps what we are looking at as we study this extraordinary visitor is not just an unusual comet. Perhaps we are looking at a piece of the process by which habitable planets are seeded with the ingredients for biology. Perhaps we are looking at the mechanism by which life, wherever it begins, becomes a galactic phenomenon rather than a local one. This idea that life's precursors can be transferred between stellar systems by physical objects is not new. It has a name, Panspermia. And it has been controversial for as long as it has existed because it seems to push the question of life's origin back a step without answering it. If the chemicals of life came to Earth from interstellar space, where did they come from before that? From another system. And before that? The regress seems infinite. But what 3I/Atlas offers for those willing to consider it is the first concrete, observable evidence that the physical mechanism for this transfer exists and operates at the scale required to matter. This is not a theoretical object. This is a real object, here, now, in our solar system, carrying chemistry from somewhere else. We can study it, we can measure it, we can learn from it. and whatever we learn will change permanently and irrevocably the way we think about life in the universe. But let us not get ahead of ourselves. Let us stay with the observations, because the observations have more surprises waiting. The rotation of 3I ATLS, as measured from its light curve over the first weeks of observation, is unusual. The object rotates. All solid bodies in the solar system rotate because angular momentum is conserved and there is nothing to stop it. But it rotates in a peculiar way. The light curve shows not one period, but what appears to be two periods superimposed, suggesting that the object is not rotating simply around one axis, but is tumbling, rotating around two axes simultaneously in a complex wobble that astronomers call non-principal axis rotation, or more colloquially, tumbling. Oumuamua also showed evidence of tumbling. The implication is interesting. Tumbling is what happens to an object that has been disturbed, an object that has experienced an impulse, a collision or an asymmetric outgassing event, or a close gravitational encounter that was not centered on its center of mass, an object that has been, in some sense, perturbed. Tumbling is common in small solar system bodies that have had complicated histories. An object tumbling in interstellar space is an object with a history that includes disturbances, which is perhaps not surprising, but it is worth noting. The color of 3I ATLS is also worth dwelling on. Colors in astronomy are not just aesthetics, they are chemistry. The color of a solar system body tells you about the composition of its surface, about what materials are reflecting the sunlight. 3I ATLS is red, not the mild reddish tint of many outer solar system objects, but an unusually deep, saturated red, what astronomers call ultra-red in the taxonomic system they use for minor bodies. Ultra-red objects are not common. They are found in the outer Kuiper belt and among trans-Neptunian objects, and their color is thought to come from a particular class of organic materials called tholins, complex polymers that form when simple molecules like methane, ethane, and nitrogen are bombarded by cosmic radiation over very long timescales. Tholins are what give Pluto its distinctive reddish-brown color at the pole, and what give the moons of Saturn their various hues. Their presence on 3I ATLS suggests, again, a history of long exposure to cosmic radiation in a cold, isolated environment. But ultra-red is unusual even for outer solar system objects. Most Kuiper belt objects are more neutral in color, reflecting a mixture of ices, silicates, and moderate amounts of processed organics. Ultra-red objects are thought to represent an older, more radiation-processed population, perhaps primordial, perhaps from the very early solar system, even pre-solar in origin. The ultra-red color of 3I-Atlas, combined with the elevated D/H ratio and the extreme eccentricity, paints a portrait of an object that is, in a very real sense, ancient. Ancient in a way that most objects we can study directly are not. Ancient in the way that meteorites sometimes are, primordial remnants that have not changed since the earliest days of their formation. The jets. We need to talk about the jets because the jets are where things get genuinely alarming. As 3I-Atlas approached the sun and its outgassing intensified, ultra-red imaging began to reveal structure in the Coma that was not uniform. There were jets, directed streams of gas and dust being ejected from specific locations on the nucleus at high velocity, creating asymmetric structures in the Coma that rotated with the nucleus's rotation period. Jets are not unusual in comets. Many comets have jets. Comet Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for 2 years, had multiple distinct jets from active regions on its surface. Comet Halley has jets. Jets are a natural consequence of having an active comet nucleus with localized regions of volatile ice exposed to sunlight. They are, in that sense, expected. But the jets of 3I-Atlas were not expected in their number, their intensity, or their effect on the object's trajectory. There were multiple jets, at least 7 distinct jet structures identifiable in the best images, and they were producing what the orbital calculation teams described as significant non-gravitational forces. Non-gravitational forces are the astronomers' way of saying that gravity alone does not explain the object's observed trajectory. Something else is pushing it. In the case of most comets, that something else is rocket effect, the recoil from outgassing, which acts like a tiny but persistent thruster, gradually modifying the orbit over time. The non-gravitational forces on 3I-Atlas were not tiny. They were large enough that the orbital uncertainty, the cone of possible future positions, was growing faster than it should have been. The more powerful the jets, the harder it is to predict where the object will be in the future. And for an object of this size, in terms of planetary defense applications, orbital predictability is not just an academic concern.
Let me be extremely clear again. 3I-Atlas is not on a collision course with Earth. The nominal trajectory, even accounting for non-gravitational forces, does not bring it anywhere near Earth's orbit in a dangerous way. But the non-gravitational forces are an active area of scientific and, quietly, in the relevant government agencies, practical concern. Because an object this size, with non-gravitational forces of this magnitude, is harder to characterize than a simple gravitational trajectory would be. And the harder it is to characterize, the less certainty there is in the long-tail predictions of its future behavior. Not that it will hit Earth, it won't, but that it might do something unexpected, that it might fragment, as comets sometimes do, that it might shed material in ways that change our understanding of what it is, that it might, in some scenario that has not yet been properly quantified, interact with the solar system in ways we have not anticipated. The fragmentation concern is not trivial. Comets fragment. It happens regularly. Comet Shoemaker-Levy 9 famously broke apart and crashed into Jupiter in 1994 in a sequence of impacts that was watched by every telescope on Earth and several in space. Comet 73P Schwarzmann-Wachmann 3 has been fragmenting for decades. Comet C-2019 Y4 Atlas, a different Atlas, a different comet, the one that had great promise in 2020 before it disintegrated as it approached the Sun, broke into pieces before perihelion and produced only a disappointing show. If 3I-Atlas fragments and the intense outgassing, the multiple jets, the cumbling rotation, and the extreme thermal stress of its rapid approach to the Sun all make this a genuine possibility rather than a remote one, then we would be looking not at one object, but at a debris field of interstellar material in our solar system to study and marvel at. A debris field of very large chunks of rock and ice moving at tens of kilometers per second, following slightly diverging orbits through the inner solar system. None of those chunks would be aimed at Earth. The probability that any individual fragment would find Earth in the tiny window of time available before they all exit the solar system is vanishingly small. But the scenario illustrates why planetary scientists watch cometary fragmentation with something beyond purely academic interest. And with 3I-Atlas, everything is scaled up. The size of the object, the intensity of the outgassing, the complexity of the jets in ways that make the unexpected seem, if not likely, at least possible.
The scientific response to 3I-Atlas has been extraordinary in its speed and coordination. Within weeks of discovery, a formal international coordination group had been established under the auspices of the International Astronomical Union, bringing together observational teams from dozens of countries to coordinate telescope time, share data, and produce joint analyses. NASA's Planetary Defense Coordination Office was involved from the beginning, not because 3I AT-Atlas posed a direct threat, but because the tools and expertise of planetary defense are directly relevant to characterizing an unusual object of this size and trajectory. The European Space Agency activated its coordination protocols. The Japan Aerospace Exploration Agency committed telescope time. China's large ground-based facilities, including the FAST radio telescope, the largest single-aperture radio telescope in the world, were pointed at 3I AT-Atlas to search for radio emissions. Not because anyone seriously expected to find artificial radio signals, but because if you have the world's largest radio telescope and an unprecedented interstellar object is nearby, you point the telescope at it. You gather every possible kind of data. You do not leave any measurement unmade if you can avoid it. The radio silence was, in its way, interesting. FAST detected nothing from 3I AT-Atlas that could be construed as artificial. The Breakthrough Listen project, the privately funded SETI initiative that uses some of the world's most capable radio facilities to search for technosignatures, also observed 3I AT-Atlas and found nothing anomalous in the radio band. This does not surprise most scientists, who would be genuinely astonished by any other result. But it is worth noting, in the context of Oumuamua's unexplained acceleration and the general sense of the unknown that 3I AT-Atlas has engendered, that the absence of an anomalous result is itself data. The object does not appear to be broadcasting. It does not appear to have a reflectivity in the optical band consistent with a metallic surface. It behaves in any of the ways we can currently test, like a natural object. A very unusual, very large, very active, chemically extraordinary natural object from somewhere very far away, but natural.
The question of where it came from, the origin question, is one of the most actively debated topics in the current literature. For Oumuamua, a backward integration of its trajectory suggested it came from the direction of the constellation Lyra, though not from any specific star in that direction that would be a plausible candidate. For 2I Borisov, the trajectory traced back more specifically to a region of sky consistent with origin from a binary star system. For 3I Atlas, the calculation is more complex because the non-gravitational forces make the backward integration less certain. But the nominal trajectory, before the complications of the jet thrust are factored in, points in the direction of the Perseus constellation, specifically toward a region of the Perseus molecular cloud, one of the nearest and most active star-forming regions in the galaxy. The Perseus molecular cloud is not a star, it is a region, a vast, cold, dense cloud of gas and dust about 1,000 light-years away that is actively forming stars right now. As you read this, it is a nursery, a place where gravity is slowly compressing clumps of gas into the density and temperature required to ignite fusion, to turn dead matter into living stars. It is one of the closest regions of active star formation to the solar system, and it has been studied extensively. It contains young protostars, protoplanetary disks, the flat, spinning structures of gas and dust around young stars in which planets form, and all the chemical richness of a molecular cloud, dense concentrations of water ice, organic molecules, complex chemistry, and conditions favorable for the exact kind of deuterium fractionation that shows up in the DH ratio of 3I Atlas. If 3I Atlas originated in the Perseus molecular cloud, and this is a hypothesis, not a confirmed fact, with significant uncertainties in both the trajectory calculation and the identification of a specific source, then its journey to us took, in the velocities involved, somewhere in the range of 1 million to a few million years. That is not long on cosmic timescales. The Perseus cloud, which began forming stars about 3 million years ago, is young by astronomical standards.
an object ejected from a protoplanetary disk in that region by the gravitational dynamics that routinely scatter planetesimals during the violent early stages of planetary system formation, could plausibly have been in transit for the entire time humanity's ancestors were walking on two legs. There is something almost vertiginous about that timeline. 3 million years ago, the creatures who would become us were just learning to chip stones. They had no language, no fire, no concept of the sky as anything other than a place where weather happened. They looked up at the same stars we look up at, but they understood nothing of what they were looking at. And at roughly that moment, or perhaps somewhat before or somewhat after, an object the size of a small city was ejected from the disk of a young star in a stellar nursery 1,000 light-years away and began its long, cold, dark transit across the void. It traveled for 3 million years without encountering anything, without any star's light close enough to touch it, in a temperature just a few degrees above absolute zero, tumbling slowly, waiting, and then it entered our solar system. And we found it, and we are trying to understand it. That is science at its most profound. That is the universe, ancient and vast, reaching across time and space to leave something at our doorstep. And the message written on that something, in deuterium ratios, in tholin colors, and volatile chemistry, in unexplained molecular signatures, is a message we are only beginning to decode. Let us talk about what we do not know, because the unknowns are as important as the knowns, and they are more numerous. We do not know the internal structure of 3I-ATLS. We know its surface chemistry from spectroscopy. We know its approximate size from its brightness and albedo estimates. We know it is active, outgassing vigorously, but we do not know if it is a solid, consolidated body like a large rock with ice mixed in, or a loose agglomeration of smaller pieces held together by gravity in their own weak cohesive forces, what planetary scientists call a rubble pile. The distinction matters enormously. A consolidated body is mechanically strong. It can survive the tidal stress of a close solar approach. It can resist the forces generated by its own outgassing. It has a definite shape in internal structure. A rubble pile is mechanically weak. It can fall apart under relatively modest stress. It can fragment in dramatic and unpredictable ways. It can behave very differently from what its size alone would suggest. The tumbling rotation of 3I-ATLS is consistent with either structure. The intense outgassing is consistent with either structure. The fact that it has remained coherent, has not obviously fragmented as it approaches perihelion, is encouraging, but it is not definitive. Many comets maintain their coherence until very close to perihelion and then disintegrate dramatically and quickly. We do not know the depth of the volatile layer. The outgassing we observe comes from the surface and near surface of the nucleus. But how deep do the ices go? Is this a thin veneer of volatiles on a predominantly rocky core, like many comets are thought to be? Or is it ice all the way down, a body that is primarily water ice in more volatile species, with only trace amounts of silicate material? The answer matters for understanding where it formed and how it evolved. A primarily icy body formed in the outer reaches of a protoplanetary disk or in the cold outer cloud of a stellar system would be very different in origin and history from a rocky body with a surface coating of interstellar ice accumulated during transit. We do not know what the unidentified molecular signatures mean. Several spectroscopic features detected in the Coma of 3I-ATLS do not match any compound in the current databases of known interstellar molecules or cometary species. There are approximately 300 molecular species that have been detected in the interstellar medium through radio and infrared spectroscopy over the past half-century. 3I-ATLS appears to contain some that are not on that list. This could mean several things. It could mean that the features correspond to known molecules under unusual physical conditions, temperature, pressure, radiation environment, that shift their spectroscopic signatures into unfamiliar positions. It could mean that the features correspond to known molecules that happen not to have been previously detected in cometary contexts. Or it could mean that the object contains molecules that have not yet been synthesized or characterized in Earth laboratories. Laboratories around the world are currently working to reproduce the chemical conditions that might generate these signatures to see if a match can be found. It is painstaking work. It may take years, and it may not yield a definitive answer, because the data from a distant comet, however high quality, inevitably has uncertainties that laboratory work has to try to bracket.
We do not know the precise size. The size estimates for 3I-ATS carry substantial uncertainty because they depend critically on the albedo, the fraction of sunlight reflected by the surface. Albedo varies widely among cometary nuclei, from as low as 2 or 3% for the darkest nuclei to as high as 10 or 15% for unusually bright ones. Most cometary nuclei cluster around 4 to 6% albedo. 3I-ATS's albedo has not been measured directly. That would require resolving the nucleus from the surrounding coma, which is required resolution that is difficult to achieve even with the best telescopes, given the density of the surrounding gas and dust. The size estimates are therefore model-dependent, and the uncertainty in size translates into an enormous uncertainty in mass, since mass scales as the cube of radius. An object twice as large is 8 times more massive. The difference between a 1-kilometer object and a 5-kilometer object is a factor of 125 in volume and mass, all other things being equal. That is a substantial uncertainty, and it matters for every quantitative question about the object's properties and behavior. There is a mission concept. It is beyond a concept, really. It has become an urgent priority to send a spacecraft to 3I-ATS while it is still in the solar system. The window is narrow, the object is moving fast, it has a defined trajectory, and once it exits the inner solar system, it will be moving too fast to follow with any spacecraft we currently have or could build on any reasonable timescale. The opportunity to make in-situ observations, to fly alongside this object, or even to land on it, or to impact it and analyze the ejecta, is a once-in-human-history opportunity. It will not come again. The next interstellar object detected may be smaller, may be less active, may be detected with less warning, or it may not come for decades. We do not know. What we do know is that 3I-ATS is here now, and the clock is ticking. ESA's Comet Interceptor mission, which has been in development for several years, was originally designed exactly for this kind of opportunity, to intercept a dynamically new comet or an interstellar object that has not previously entered the inner solar system. It is currently in development and testing, with a launch window in the late 2020s. It is not ready to intercept 3I-ATS. The timeline does not permit it. But Comet Interceptor's existence demonstrates that the scientific community anticipated this kind of opportunity and was trying to be ready for it. The lesson of 3I-ATS may be that trying to be ready is not enough, and that a standing rapid response capability for interstellar objects, spacecraft ready to launch on short notice, pre-positioned in orbits that can be adjusted to match a variety of interstellar trajectories, is not a luxury, but a necessity.
In the absence of Comet Interceptor, several teams have proposed rapid, lower-cost missions using existing technology. The ICE-3 concept, repurposing an existing spacecraft or adapting a CubeSat bus to perform a fast flyby, has been floated. The SpaceX Starship, which dramatically changes the mass-to-orbit economics of space launches, has been mentioned as a potential platform for a quickly assembled interception mission if the scientific payload could be designed and tested on the necessary timescale. The challenges are extraordinary. The object is moving at tens of kilometers per second relative to the Sun. The trajectory must be matched precisely, the spacecraft must survive the radiation and impact environment near a highly active comet, and the scientific instruments must be able to acquire data and transmit it before the flyby geometry makes communication with Earth difficult. None of this is impossible. All of it is hard. All of it takes time that 3I-ATLS is not waiting to provide. As of the time of writing, no mission to 3I-ATLS has been approved. The discussions are ongoing at NASA, at ESA, at JAXA, at the private space sector level. The urgency is recognized. The will is there. The question is whether the bureaucratic, engineering, and logistical machinery of human spaceflight can accelerate fast enough to meet the universe's schedule. The universe, as I have noted, is patient, but in this particular case, it is not giving us much time. The public response to 3I-ATLS has been interesting to observe. When the discovery was announced, initially through the Minor Planet Center's standard channels, then amplified by the IAU announcement and the social media activities of astronomers who understood what they were looking at, the response was significant, but not panicked. The name helped, paradoxically. 3I-ATLS sounds like a catalog entry. It does not sound like a threat. The early headlines varied wildly, from cautious scientific reporting to breathless tabloid speculation about alien probes and interstellar invasion. None of the responsible scientific communications suggested anything artificial, but the memory of Oumuamua's unexplained acceleration and the controversy that surrounded Avi Loeb's speculations about that object meant that the words interstellar object now come attached in the public imagination to a certain shimmer of exotic possibility.
That shimmer is understandable. That shimmer is, in fact, part of what makes science compelling. The possibility that our solar system is not just a local pond, but a destination, a port of call for objects from the wider galaxy, engages something deep in the human imagination. We want to know if we are alone. We want to know if the universe is inhabited. We want to know if the chemistry that led to us, to consciousness, to science, to the capacity to wonder about these things is unique or common. 3I Atlas does not answer any of those questions directly, but it opens a door. It demonstrates concretely and observably that the galaxy is connected, that objects can travel between stellar systems, that chemistry can be shared across the void, that what happened in a star-forming region 1,000 light-years ago, 3 million years ago, can arrive in our solar system as a measurable, analyzable object. The galaxy is not a collection of isolated systems, it is a community, a diffuse, slow, impersonal community, but a community nonetheless. The implications for the search for life are profound, though they require careful handling. If 3I Atlas is carrying organic chemistry from the Perseus molecular cloud, chemistry that is demonstrably more complex and varied than what we find in typical solar system comets, then it is possible that the molecular precursors of life are more widely distributed and more efficiently transferred between stellar systems than our existing models suggested. The Panspermia hypothesis, in its most literal form, the idea that life itself, living microorganisms, might travel between stellar systems, remains highly speculative and faces formidable barriers. The radiation environment of interstellar space is lethal to known life forms on any timescale relevant to interstellar transit. The temperatures approach absolute zero. The transit times are millions or billions of years.
living organisms, even the most radiation-resistant, cold-tolerant extremophiles known, cannot survive these conditions for these durations. This is not a statement of defeat, it is a statement of physics. But the chemistry of life, the molecular building blocks, the precursor compounds, the organic scaffolding from which biology assembles itself, given liquid water in energy and time, is far more durable than life itself. Amino acids have been found in meteorites. Nucleobases, the components of DNA and RNA, have been detected in space. Complex organic molecules, including the building blocks of the sugars that form the backbone of nucleic acids, have been synthesized in laboratory simulations of interstellar ice conditions. These molecules can survive in solid form for billions of years. They can be incorporated into planetary bodies. They can be delivered to young planets by cometary impacts. And now, with 3I Atlas, we have evidence that objects carrying such chemistry can cross from one stellar system to another, not just within our own galaxy's quiet suburbs, but from the dynamic, molecule-rich environments of active stellar nurseries. If this kind of delivery is common, and our models suggest that the number of interstellar objects passing through the solar system is large, with estimates suggesting thousands of such objects of 3I-ATLS's size class should cross the solar system every million years, then the chemistry of life is, in a very real sense, galactic property. It belongs to no particular system. It propagates, it spreads, and the conditions under which it can eventually give rise to biology exist not just here, not just in our solar system, but wherever a planet with liquid water and an energy source receives the right chemistry from the cosmic commons. The universe, on this view, is not a collection of isolated chemical experiments. It is one experiment, very large and very old, running in parallel across billions of star systems, seeded by the same materials, nudged along by the same physics. This is, to be clear, a hypothesis, a compelling and increasingly well-supported hypothesis, but a hypothesis. Science requires evidence, and the evidence is still accumulating. 3I-ATLS is the most significant single piece of evidence yet gathered, not because it proves any of this, but because it makes it physically, chemically, observationally real in a way that theoretical models and meteorite analyses alone cannot. This is an interstellar object, here, now, in our solar system, and we can study it directly. Whatever we learn from it will be real data about a real object from another stellar environment. That is unprecedented, and it will feed into our models of planetary formation, of chemical evolution, of the habitability of the galaxy, and of the probability of life beyond Earth in ways that will be felt in the scientific literature for decades. Let me take a step back, because this is the kind of moment that calls for perspective. Not just the perspective of science, but the perspective of history. Of all the things that humanity has discovered about the universe, and we have discovered an extraordinary amount in a surprisingly short time, perhaps the most profound is the discovery of our own context. We live on a small, rocky planet, orbiting an ordinary star, in a galaxy of 400 billion stars, in a universe of 2 trillion galaxies. We know this, we have known the broad outlines of it for decades, and yet knowing it and truly feeling it in your bones are different things. The data have told us that we are not central, that we are not special in any cosmic sense, that the physics that governs our existence governs everything, everywhere. But for all that knowledge, the solar system still felt, at some level, like home, a familiar neighborhood, our neighborhood, the 8 planets, the asteroid belt, the Kuiper belt, the Oort cloud, ours, familiar territory. 3I Atlas changes that, in a subtle but important way, because it brings the outside in. It makes the solar system a transit zone, a way station on a route between stellar environments. It makes our neighborhood not a sealed container, but a point on a network. And if it is a point on a network, If objects are routinely traveling between stellar systems, carrying chemistry and physical information, connecting the galaxy's various environments, then everything changes about how we think about our place in the cosmos. We are not isolated. We are connected. The connections are slow and vast and impersonal, but they are real and they are physical, and they carry information. And perhaps, just perhaps, they carry more than chemistry. Perhaps they carry, encoded in their molecular inventories, the universal language of prebiotic chemistry, the library of the cosmos, written in deuterium ratios and organic molecular signatures and tholin codings, available to any planet lucky enough to intercept the right object at the right time. Earth intercepted something once. Many times, actually, during the period called the Late Heavy Bombardment, roughly 4 billion years ago, when the solar system was still settling into its current configuration and impacts from comets and asteroids were frequent and violent. The Earth was bombarded with water and organic chemistry from the outer solar system. That bombardment may have been what gave Earth its oceans. It may have been what delivered the organic chemistry that eventually led to the first self-replicating molecules, the first cells, the first life. This is not certain. The origin of life on Earth is one of the great unsolved problems of biology and chemistry, but it is consistent with the evidence. And if 3I Atlas is representative of a class of objects that contributes to that kind of bombardment, if interstellar objects routinely deliver exotic chemistry to young planetary systems, then the ingredients that started life on Earth may have come not just from the outer solar system, but from another stellar system entirely.